Can you see my screen?
Yes, ma'am.
Okay, so before we start for today, for tomorrow, for the exam next week, your exam date is on Tuesday. It will start from, let's say, 10:15 and go up till 11:30. The paper will be on Google Forms most likely. We will send you an email about that. The syllabus is only up to regular languages. Things from context-free languages will not come. It will be only up to regular languages. And also we'll be very strict if we will be checking. So if we see there is any copying, then straight away everybody involved will be getting -5 in that question. Yeah, anything, all other details we will send to you by email. Okay, so let's start with parse trees.
Ma'am?
Yes?
Ma'am, so DFA minimization is also a part of the syllabus in the regular
Yes.
language? Okay.
Yes. Up to Myhill-Nerode theorem.
Okay, thank you.
Yeah. Okay, so let's start off with parse trees and pumping lemma for context-free languages. So as in regular languages, we were interested to see what is the bound for computation. Are there any languages which cannot be computed by finite automata? Similarly, here we want to see what are the kinds of languages which are not context-free languages, which do not have context-free grammars. And a related topic in order to understand pumping lemmas and the reason or the proof for the pumping lemma for context-free languages, we have to understand parse trees. Okay, so what is a parse tree? You consider a context-free grammar G, which can be written as n sigma ps. A parse tree will be for a particular sentential form of this grammar. So let's see what it is. There are a few properties. It's basically a tree. In terms of graph theory, it is a tree with the following properties. If you consider every vertex of the tree, that vertex will be labeled by some symbol from n union sigma union epsilon. It could also be labeled by epsilon, but it can also have labels from non-terminals or terminals. The root specifically has to be labeled by the start symbol. Also, if you consider an internal vertex or an interior vertex, that is a vertex that is not a root and not a leaf, then they must be labeled by non-terminal symbols. This is a criteria for the parse trees. Now consider a vertex V and suppose it is labeled by some non-terminal A. Consider its children. Suppose it has n children and their labels, suppose they are labeled x1 to xn in the parse tree. That means that there must be a production in P such that of the form A going to x1 to xn. Okay, so basically suppose you have a vertex which is labeled by A, this is V, and suppose it has children V1 to Vn, and these are labeled x1 to xn. So essentially you know that you have a production A going to x1 concatenated up to xn. Okay, and the final point is if a vertex is labeled with the symbol epsilon, then it must be a leaf. It cannot be the root, nor can it be an interior vertex. It must be a leaf, and it will be the only child of its parent. So the parent vertex of a vertex labeled by epsilon has degree 2. At most 2. It can have its own parent, but it has at most one child. It has exactly one child, the child labeled by epsilon. So notice that by these criteria, the leaves can have labels from n union sigma union epsilon. The leaves can be labeled by non-terminals, terminals, as well as epsilon. The interior vertices must be labeled by non-terminals and the root vertex must be labeled by S. These two things are a must. But the leaves could have symbols from n union sigma union epsilon. And also this criteria ensures the relation between a vertex, the label of a vertex and the label of its children. Now, if we order the leaves of the tree from left to right, and we can get it by restricting to the order. So you first do an in-order or a pre-order, and then you try to extract the ordering of the leaves. You extract only the subsequence, which consists of vertices that are leaves. That will give you an ordering of the leaves of the tree from left to right. So if we only consider the ordering of the leaves from left to right, this will give me a sentential form, uh, uh, that is derived from S. So this is not a formal proof. You can prove it for yourself by induction. And basically this sentential form is being represented by T. So suppose you start with S, you have some tree, you have this node labeled S, then you have some tree, and you just read the leaves from left to right. So let's call this A, B, B, or something like this. Then the claim is that you have a derivation from S to the sentential form AABB. And you can prove this by induction. And obviously, if the leaves are labeled by sigma union epsilon, you consider the leaves. If there are no non-terminals present in the left to right ordering of the leaves, then it is a sentence of L of G. So this is how past trees are related to the sentential forms derived from the start symbol S, and in particular the sentences derived from the start symbol S. So here is an example of a past tree for the specific string a cube b cube. So we know that for the language a to the n b to the n greater than equal to 0, we had the context free grammar s going to asb epsilon. We also saw a grammar in Chomsky normal form, but let's consider this simple version, s going to asb epsilon. So in order to get a cube b cube, this can be a pass tree. You start with S, and the children of S are labeled A, S, B. Then you take this particular S. Notice that A and B cannot have any children because they are terminal symbols. Internal vertices can only be non-terminal symbols. So again, this S could have some children. We are adding the children A, S, B again. Again, this S we are making into an internal vertex by adding the children A, S, B, and this S has a single child labeled by epsilon. Now, if you look at the ordering of the leaves from left to right, it's going to be A. I've left out the epsilon because that doesn't matter. B. Everywhere that an epsilon comes in the string itself, you can just collapse that part. So it comes out to be A, B. Similarly, if I wanted a pass tree for this balanced parentheses expression, recall that the parentheses grammar was S going to bracket S bracket, left bracket S right bracket, or SS or epsilon. And this is a pass tree that I can, this is a pass tree corresponding to this particular expression. I take S as my root. Now I create two children, both labeled S and S. The first S I make into an internal vertex that has children left bracket S and right bracket, and this S again I have a single child labeled epsilon. Similarly here I do the same thing, and I come down to the single child epsilon, and if you read from left to right, the leaves will read exactly the expression given to you. So you can notice that if I just go from S downwards, basically I am getting a derivation S going to SS, and then I replace the first S with bracket S, keep the second S, replace the second, again replace the first available S, I replace S by epsilon, second S I keep as it is, I these are terminal symbols. Now I look at the first non-terminal symbol available to me. It's this S. Now again I look at its children. I have basically used a production that says bracket S bracket. Again I look at the first available non-terminal symbol from the left. Using this is that symbol. I again put it as sorry, this is that symbol, and I again put an epsilon, replace it by epsilon, and I have, oh no, sorry, this is that symbol, and I get this using its children. And finally I look at uh, the leftmost available non-terminal symbol. Using this portion, I replace S by epsilon and I get this expression. I don't have any other non-terminals left, and therefore I have derived the left to right ordering of the leaves. So this is sort of the relation between the derivation of a sentential form and the parse tree itself. So you can think of it as two ways of deriving. If I can talk about leftmost derivation, which means that at each step of the derivation, starting from the start symbol S, a production will be applied to the leftmost non-terminal. So if I was at a step where A was replaced by W1B, W2C, let's say, then in the next step, let's say B is the leftmost, so here B is the leftmost symbol. Then I will be replacing B, I will be looking at a production where B is going to be replaced by something else. So this is leftmost derivation. Similarly, you can have rightmost derivation where suppose A was replaced by W1B, W2C. So W1B, W2C got derived from A. Then in the next step of derivation, I'm going to be trying to replace C, the rightmost non-terminal symbol. So this is the concept of leftmost derivation and rightmost derivation. So notice that if I do a pre-order traversal of a parse tree, then this will correspond to a leftmost derivation of a sentential form. Just as I said earlier, over here, what were we doing? From S, I started from S. Its children showed me that the first step of derivation is S going to SS. Next, the first child, if you look at the ordering, the first child, if I replace the first child, it's going to give me its children is going to give me the second step of derivation. Next, I looked at this and I looked at its children. I could replace it by epsilon and I got the like the two leftmost leaves. Now I am left with another non-terminal symbol, which was the second child of the root, and I kept replacing the leftmost available non-terminal symbol. So therefore, if you do a pre-order traversal of the parse tree, then this corresponds to a leftmost derivation of the sentential form corresponding to the left to right ordering of the leaves of the tree. And this will be unique to the parse tree. If you fix a parse tree, then the leftmost derivation will be unique for that particular sentential form corresponding to the parse tree. But if you give me a sentential form, there could be more than one non-isomorphic parse trees. So in particular, if I give you this particular expression, can you give me another non-isomorphic parse tree for this expression from the grammar? Or maybe another, if you just give me another derivation for this particular expression, then we know that we can look at the parse tree corresponding to that derivation. So this parse tree correspond. Yes.
Ma'am, we can construct the rightmost derivation, but that would also give the same parse tree, right?
Rightmost derivation that will give the same parse tree. Isomorphically, it will be the same parse tree.
Yes, ma'am.
But if we follow the same, okay. So over here, I am talking about two leftmost derivations for the same sentential form. It is possible that there could be two leftmost derivations for the same sentential form, which result in non-isomorphic parse trees. No, I'm not comparing a leftmost derivation and a rightmost derivation. In this case, it turns out to be isomorphic, but I'm not comparing leftmost and rightmost derivations. I'm comparing leftmost derivations and their parse trees.
Okay, ma'am.
Yeah. Can you give me another left? So this I will be calling as a leftmost derivation, because at every step I'm looking at the leftmost available non-terminal symbol and applying a production to that. At every step I'm doing this. Can you give me another such derivation for this same expression? So let's say, just to start off, if I had given S go into bracket S, can you derive this from here?
Ma'am, it can't be derived that way, right?
Why not? If I did this, oh, hold on, 1 minute, 1 minute. One minute, 1 minute, maybe not this example. Just give me 1 minute. Okay, maybe, and sorry, not this example. Let me just try another example. So suppose I gave you this expression, just this much. So one way is S going to, I follow the same thing, S going to SS, and then I do SS. Right, I can do this. Every time I'm replacing, so here this is the leftmost available non-terminal, here this is the leftmost available non-terminal, then this, and then finally here this is the leftmost available non-terminal, and we arrived at this. Notice that we can also do the following. This is also a leftmost derivation, right? So in this particular case, if I just wanted to derive this, if you look at the trees for each of them, let me just quickly draw the trees. So you have S, and then you have S and S. Okay. So this is one tree and the other one is S. Right. So just if you compare the number of vertices there itself, you will see that this is not an isomorphic to this. This is actually becoming a subgraph of this. Okay, so there are actually two parse trees corresponding to the same string. So if you have, it is possible that a sentential form or even a sentence can have more than one more than one non-isomorphic parse trees, and therefore more than one leftmost derivations. So if a sentence has two leftmost or two rightmost derivations in the given grammar, then that particular grammar is called an ambiguous grammar. And if this is true, suppose there is a context-free language such that no matter which grammar, you can have more than one grammars for the same context-free language. Suppose each of these context-free grammars is ambiguous, then this will be called an inherently ambiguous context-free language. And if a context-free language, suppose there exists a context-free grammar that is not ambiguous, then it is called unambiguous. So in particular, if you look at this example, can you tell me whether it is ambiguous or unambiguous? This particular grammar.
Unambiguous.
Can you give me a proof for why you're saying it?
Ma'am, if two different derivations exist, then like if the number of steps in both the derivations are same, then because there is only one s in the derivation, then the two exact derivations will be exactly the same. And if the number of steps are different, then one will have a greater number of characters than the other, which is a contradiction.
Correct. Yeah. That is the basic idea. So if you can, because of the types of productions, you can relate the number of terminal symbols with the number of steps that are in the derivation. So if the number of steps in the derivation is let's say 1, then and you end up with a sentence at the end of the derivation, then you know that the string can only be epsilon. If it is 2, then you know it can only be AB, and the second step must be S being replaced by epsilon. Every time, if I'm not applying the epsilon at every step, I have exactly one non-terminal to replace. If I replace it by epsilon in the next step, then I have found a sentence. I have found a sentence. And if I do not replace it by epsilon, then I'm increasing the number of terminal symbols in my current sentential form. So therefore, this is broadly a sketch of the proof that this particular grammar is unambiguous. If you give me a string, I can give you exactly one leftmost derivation for that string. Okay, so now we will come to, this was to show, this was to visualize in a certain way the derivation of a sentential form from the from the start symbol. Now, can somebody tell me if I had, we've also learned normal forms, right? So if I have my grammar in Chomsky normal form, meaning that L minus epsilon is in the grammar for L minus epsilon is in Chomsky normal form. And I also have this S going to epsilon. One extra production I have to generate epsilon. Can you tell me what the parse tree is going to look like for any sentential form that can be derived from S?
And binary trees.
Correct. It will be a sub, yeah. So every every node can have at most 2 children. Every internal vertex can have at most 2 children. So if you are in Chomsky normal form, you have further structure on the parse trees, and this will be crucially used to give a pumping lemma for context-free languages, which can again be used similar to pumping lemmas for regular languages. Pumping lemma for context-free languages can be used to detect whether a language is context-free or not. So let's get into this. The claim is, this is the statement of the lemma, that for any context-free language A, there exists a k greater than or equal to 0 such that you take any z in A that is of length at least k. It can be broken into 5 substrings u, v, w, x, y, where v and x, at least one of v and x is not empty. Vx cannot be the empty string. At least one of v or x is not empty. And the total length of vwx is at most k. If you consider, so there will exist such a set of 5 substrings with these properties, such that you take any I and you pump up v and x simultaneously. So if you consider u, v to the I, w, x to the I, y, this new string will also belong to A. So notice the difference from the pumping lemma in regular languages in the fact that v and x are being simultaneously pumped up. There are 2 places where you are pumping 2 disjoint substrings which you are pumping up. Okay, they are separated by this string w. So again, just to repeat the lemma, you take any context-free language A. The claim is that there exists a k such that you take any string of length at least k. It can be broken into 5 substrings u, v, w, x, y with some additional properties that either v or x must be non-empty, and vwx is the length of vwx is at most k. And now if you give me any I pump up v and x simultaneously, the new string u, v to the I, w, x to the I, y will belong to the same context-free language. Okay, and I is greater than or equal to 0. So even if I threw out v and x, so even the language u, w, y, this belongs to A as well. Okay. Anybody has any idea why this is true? For regular sets, this k basically acted as, for regular sets, I know that there exists a DFA, and therefore this k basically corresponded to the number of states in the DFA. Any ideas how we can make such a claim for context-free languages? We don't exactly have a machine model yet for context-free languages. Okay, so this is where we are going to be using parse trees again. So let's consider the Chomsky normal form for the language A minus epsilon. So then a parse tree for a string Z will basically be a binary tree. So if Z is long enough, binary tree means every vertex has at most 2 children. So if Z is of length k, if it's long enough, then there must be a path which is long enough. So if Z is of length k, then the parse tree will also have a long enough path. We will look into what this long enough means. Now, if I have a very long path, then we will try to apply pigeonhole principle to show that there are at least two occurrences of the same non-terminal symbol. So there will be some non-terminal symbol. The path will be that long that there will be some non-terminal symbol A that appears two times on the same path, that corresponds two times on the same path, let's say. So you have, let's call them A1 and A2. The occurrences are A1 and A2. Now you look at the trees that are subtrees rooted at A1 and A2. Let's call them TA1 and TA2, denoted by the orange tree and the green tree. So now at A2, if I just threw out the subtree TA2 and replaced it by the subtree TA1 again, this does not violate the conditions of a parse tree. So this is a new parse tree. But if you notice, look at the string formed. This particular, if I now call this X, sorry, how did I start? With U, right? If I call this portion U, this portion V, this as W, this as X, and this is Y. Then notice that what happened over here, you still have U. Over here, you have V. Instead of W, you got this entire tree, right? The leaves of TA1 is basically VWX. So here you have VWX, and then again here you have X, and then here you have Y. So notice that you have two copies of V and two copies of X at the same time. So you boosted it. This is the idea. So if you have two copies of the same non-terminal along the same path, then the lower tree can be replaced by this upper tree, by a copy of the upper tree again, because I have the same non-terminal, so I can repeat whatever children were appearing over here. I can just do the same copies at the second copy at A2, and therefore I will have the same tree in this format. And if you just look at the leaves, the breakup of the leaves as U, V, W, X, Y, then V is getting repeated again in the lower tree and X is getting repeated again in the lower tree. So this is the idea. Now let's get into the formal proof. So let n be the total number of non-terminal symbols. Then I'm going to take k to be 2 to the n plus 1. So obviously by now you should have figured out why I'm taking it like that. So if z belongs to, take a z that belongs to A and has length greater than equal to k. Okay, so then this must be I am in Chomsky normal form. So this must be, the parse tree must be a tree which has at least k is 2 to the n plus 1. It has at least 2 to the n plus 1 leaves. Right? Because the leaves have to read out z. So it must have at least 2 to the n plus 1 leaves, which means the depth of the parse tree, since it is a binary tree, the depth of the parse tree must be at least n plus 1. Now if you consider the longest path in the parse tree, then it has at least n plus 1 non-terminals, because each of the internal vertices are non-terminals. So it has at least n plus 1 non-terminals. And of course, by pigeonhole principle, that means that some non-terminal appears twice in the path. If you go from bottom upwards, look at the first non-terminal, let's call it A, that occurs twice in the path. So now you take the two occurrences of A that are farthest from the root. So you are going bottom up and you look at the first two occurrences of A on the path, going from leaf towards the root, towards S. So as I said before, this Z, the breakup of Z into U, V, W, X, Y will be as follows. W is whatever is generated by the lower occurrence of A. So the subtree rooted, the leaves of the subtree rooted at A2. VWX is generated by the subtree rooted at A1, and UVWXY is the total string generated from S. So each node will have at least one child because this is in Chomsky normal form. Chomsky normal form means each production is of the form A going to A or A going to BC. So you cannot have empty, it must have at least one child. You don't have anything of the form A going to epsilon. There is at least one child, therefore it must be true that either V or X is non-empty. Because from each of these A's, there will be at least one child coming down. Let's call the tree rooted at A1 T1A and A2 T2A. If I replace T1A by T2A, meaning that the upper tree is replaced by the lower tree, I replace the orange tree by the green tree, then notice that I have obtained UWY, which is U V to the 0, W X to the 0, Y. At the same time, in the same way, if I replace T2A by T1A, meaning the lower tree by the upper tree, the green tree by the orange tree, then the string generated by the leaves from left to right is U V square W X square Y. And if we repeat this, if we repeat the replacement of the lower tree T2A by T1A k times, then we will be getting U V k plus 1 W X to the k plus 1 Y. Lastly, we had a condition that VWX must be of length at most k. And why is this true? Because we are choosing A to be the first non-terminal symbol from the leaf upwards that appears 2 times. So TA1 can have at most n plus 1 height. If it was more than n plus 1, then there should be some other non-terminal appearing twice within that subpath. So height of TA1 can be at most n plus 1, and therefore this can have at most 2 to the n plus 1 leaves. 2 to the n plus 1 is k. So VWX was the number of leaves, corresponds to the number of leaves of TA1, and we have bounded the number of leaves in TA1. So therefore, we have shown we have proven the statement of the pumping lemma that you give me any context-free language, there exists a k. This k is basically related to the exponent of the number of non-terminals in the grammar. There exists in a particular grammar for the language, there exists a k such that you give me any string of length at least k. This can be broken into 5 parts U, V, W, X, Y, such that there are some conditions, 5 parts where there are some conditions on V, W, and X. Either one of V or X must be non-empty, and V, W, X together has length at most k. If you give me, if you look at this particular partitioning, you can give such a 5 partitioning of Z such that you will be able to boost V and X simultaneously by any I going from 0 to 1. So you could delete V and X simultaneously, or you could put in more than one copy of V and X simultaneously. And the new string generated is going to be in the same language, A. And the reason why we can say this is because of the parse trees. Look at a parse tree in the context-free. Consider the grammar to be consider the grammar to be in Chomsky normal form. Look at a parse tree under that grammar for this particular string Z. I am saying Z is long enough that the number of Z is long enough such that there is a long enough path in the parse tree. And by long enough path, I mean there are at least, in that path, there is at least one non-terminal symbol that is repeated twice. And if it is repeated twice, then look at the subtrees at the 2 occurrences. I could replace one with the other. And with this replacement, I'm going to be boosting this V and X simultaneously or deleting them simultaneously. Okay. Any questions? Any questions regarding the proof? So how are we going to use the pumping lemma for context-free languages? Similar to regular languages, the sufficient property that a language is not a context-free language is by taking the opposite statement. If you give me any k, for all k greater than equal to 0, there will exist a z of length at least k, such that no matter how you break Z into 5 parts, U, V, W, X, Y, where these 5 parts satisfy the fact that either V or X is non-empty and V, W, X is at most K. You give me any such 5 partitioning with these satisfying these two properties, there exists an I such that U, V to the I, W, X to the I, Y, this new string does not belong to A. If you can prove this for some language, you can show that this language is not context free. So again, we can look at it as an adversarial game. So the adversary will be picking a k. You will be allowed to pick the string z of length at least k. But now the adversary will pick the 5 partitioning of the string z. Of course, with this particular condition satisfying, the 5 partitioning should be satisfying these two conditions, that either V or X will be non-empty and VWX will have length at most K. Now you are allowed to pick the I and you win if U, V to the I, W, X to the I, Y does not belong to A. So this is the adversarial model of trying to use pumping lemma to show that a language is not context free. Okay, any questions so far? Then we'll go into the example. So let's look at an example. We saw that a to the n, b to the n, such that n is greater than equal to 0 is a context-free language. But if I do a to the n, b to the n, a to the n, all three are n's, such that n is greater than equal to 0, this is not a context-free language, and we can show this by using by a direct application of the pumping lemma. So suppose the adversary gives you k, you pick the string z, which is a to the k, b to the k, a to the k. So the length of z is at least k. Now the adversary will be picking a 5 partitioning that satisfies these two conditions. So the argument is, if you pick I equal to 2, then no matter what the partitioning is, you will be winning. So what can the partitions be? No matter how the adversary breaks it up, the first case is one of V or X has at least one A or at least one B. And at least one B. So either V or X has a mixture of A's and B's. In that case, if I boost it up by 1, if I pick I to be 2, then the form A star, B star, A star will itself be violated. So automatically it's not in A. It's not in this language A to the N, B to the N, A to the N. Second case is both V and X only. So now after case 1, it must be the cases must be that V and X are purely of one particular symbol. It is possible that they are V or X. So it is possible that V is purely of A, X is purely of B, or V and X both are purely of A, or both are purely of B, or V is purely of B, X is purely of A. But you cannot have a mixture because you have dealt with the mixed case in case 1, where you say that the form itself is going to be violated if you boost up V and X by 1. So the second case is V and X both have only A's. In the same way, you can argue if V and X both have only B's. If it has only A's, then the number of A's, the relation between the number of A's and number of B's will be violated. In the language, it must be true that the number of A's is exactly 2 times the number of B's. And similarly, in perspective of B's, the number of B's will be exactly half of the number of A's. But if you boost V and X simultaneously, the number of A's will become more than twice the number of B's in the new string. So that the new string cannot belong to the same language. Similarly for B's. The remaining cases, one of V and X has only A's and the other one has only B's. Then again you can show that the form of the structure of the string will not be of the form A star B star A star. Will not be of the form A to the n, B to the n, A to the n. You will not be able to maintain the same number of like you will not be able to either maintain the number of A's with respect to B or the alterations between A and B. So therefore, we have been able to give a winning strategy. When I pick I to be 2, I can give a winning strategy for the pumping lemma and show that A to the n, B to the n, A to the n, this language is not context free. Any questions? Okay, so let's look at another one. A equal to WW. W is in A, B star. So this also is not a context free language, and this will not be a direct application of pumping lemma. There is one more step to it. So what we will show is that what we will be using is that we will be looking at the restricted language A dash, which is A to the n, B to the m, A to the n, B to the n, a very particular form of the language. So this is basically A intersection L of A star B star A star B star. Now notice that L of A star B star A star B star is a regular set. Now here is a fact which you will later be able to prove. For now you just take it as a fact. The intersection of regular sets and context-free languages are context-free languages. For now you take it. When you learn of an equivalent machine model for context-free languages, you will be able to prove it yourself. So the intersection of regular sets and context-free languages are context-free languages. So this is a regular set. Suppose A was a context-free language, then A dash would be a context-free language. So if we can show that A dash is not a context-free language, then I am in effect showing that A is not a context-free language. So the aim is to show that A dash is not a context-free language. I'll just give you the strategy. If the adversary gives a k, then you pick the string A to the k, B to the k, A to the k, B to the k. And again, by a similar argument, if you pick I equal to 2, then no matter how you break up, how the adversary breaks this string into 5 parts with satisfying these criteria, you will always win. So you can work the steps out. It will be similar to the previous argument, but the strategy was as follows. I am showing that a separate language, a subset of the actual language, is not a context-free language. And the reason why this works is if this is the intersection of a regular set and our given language. If this was a context-free language, or if this was a context-free language, if our language was a context-free language, then we know that the derived language is also a context-free language. But if we prove that the derived language is not a context-free language, then our language cannot be a context-free language because of this fact. So this is also a strategy to, it's not a direct application of pumping lemma. We are applying pumping lemma to another language, an auxiliary language, but we are still being able to show that our particular language is not a context-free language. Okay, now we come to a very interesting result for context-free languages. So we knew that regular languages are closed under complementation. But the same thing is not true for context-free languages. So if you consider the complement of the previous language, A, which was WW such that W belongs to AB star, if you consider this language, I can give you a context-free grammar. So let me tell you what the productions are, and then I'll explain why this is leading to the production of the derivation of A, all strings in A bar. So the production is, you start with, your start symbol is S. From S, you go to two non-terminal symbols AB or BA or A or B. Now A you have productions from A to CAC. C is a non-terminal and a terminal symbol or a terminal symbol A. Similarly, for B, you have CBC or non-terminal symbol B. And from C, you can generate either non-terminal symbol A or B. Okay, so now what's the explanation for the productions, these productions resulting in the language A bar? So S going to S deriving non-terminal symbol A or B will basically generate all the odd strings. Notice that A bar will contain all odd strings, just trivially, because WW is an even string. All odds, there can be no odd strings in this language, which is A. So all odd strings must be generated, and the claim is S will be generating all odd strings. Why? Because A generates, if you look at A, it is generating strings of the form XAY, where length of X is equal to length of Y, and you have an extra A. So this is an odd string, odd length string. Similarly, B will generate strings of the form UBV, where U and V are of the same length. This C is ensuring, I don't know how these two C's are finally, like, they are behaving independently. This C could finally end up as an A, this C could finally end up as a B. But I know that anything before this, but any non-terminal symbols derived before this non-terminal symbol A will be equal to the number of non-terminal symbols derived after the non-terminal symbol A. So length of X is equal to length of Y. And similarly, length of U is equal to length of V. So S going to A and B will be generating all the odd strings. Now, notice that the remaining strings in A bar are going to be all those strings such that if you consider, let's say it's of the form X, A, Y, U, B, V, where X, length of X plus length of V is equal to length of Y plus length of U. So meaning that the length of Y and U is so let's say XA, Y, B, V, this length was L. Length of Y, U is L by 2. Meaning that you look at the position at which X is in X, A, Y, and you look at the position at which B is in U, V, B, the positions are the same. And one is different from the other. So, and it could also be the other way around. It could be UBV XAY. So B and A, if you look at UBV and XAY, then the claim is that B and A are the positions where it's not the same. This is where it's not of the form WW. And how are we generating such strings? We are generating with the productions S going to AB and AB or BA. So S going to AB will generate strings of the form XAY UBV, where X is equal to Y and U is equal to V. And okay, so what I said earlier is wrong. Okay. Let me just finish this and then I'll go back to this again. We are going to be generating AB and we are going to be S going to AB is going to generate strings of the form XAY UBV, where X is equal to Y and U is equal to V. Or of S going to BA is going to generate strings of the form UBV XAY. Now, if I look at XAY UBV, what I will not break it as XAY and UBV. All I will say is that this string is of length L and YU is of length L by 2. So this breakup could happen anywhere, but this distance between A and B is L by 2. And that means that if you look at the position of A and the position of B, this distance is L by 2, which means that there is a flip between if you look at these positions, they should have matched in WW, but over here this is a pair that is witnessing that it is not of the form WW. Notice that in WW, you look at any two positions that are at distance L by 2 from each other. They should match. They should be matching. That is a distance exactly L by 2, they should be matching. But this is a pair that is witnessing the fact that this is not of the form WW. I'm not going to particularly say that X say Y is going to be of the form W and U, B, V is going to be of the form W. Forget that. I'm just using the property that in WW, if you look at two positions that have exactly distance L by 2, then they should be of the same, they should have the same symbol. But these are strings where there are at least two positions that are at distance exactly L by 2, but they have different symbols. So they are witnesses of the fact that this is not of the form WW. And S going to AB and S going to BA are going to generate strings of this form. Okay, and the claim is that any string in A bar must be of one of the above two forms. So if it is an odd string, so A bar can have either, will have all odd strings, because WW can only be of even length. A bar must have all odd strings. If it has strings of even length, then it must be the case that these strings have at least a pair of positions at distance exactly L by 2 from each other, and where either it is A and B or B and A, where the two symbols are different. This is what will witness that they are even strings not of the form WW. Therefore, these are the two kinds of two subsets of strings in A bar. So this set of productions is generating A bar. A bar is a context-free language, whereas we just proved that A is not a context-free language. So context-free languages are not closed under complementation. So then let's continue with the closure properties. For union, if you have G1 and G2 to be grammars of this form, then G1 union G2 could just be obtained by adding a new start symbol S, a new non-terminal symbol S, which will be our new start symbol. And if S1 and S2 were the respective start symbols of G1 and G2, then I'll just add a new production where S goes to S1 or S2. Similarly, for concatenation, again, I will add a new symbol, non-terminal symbol S, make it a start symbol, and I'll add a new production S going to S1 and S1 concatenated with S2. This is not concatenation, but S going to S1, S2. What about intersections? So we can show, here is an example where we can show that context-free languages are not closed under intersections. So if you consider this language, A to the N, B to the N, A to the M, N and M are both greater than equal to 0, and A to the M, B to the N, A to the N, N and M again greater than equal to 0, and take the intersection of these two languages, then it is A to the N, B to the N, A to the N, which we already showed is not a context-free language. Can somebody show me that these two languages are context-free? They are very similar, so if you get one, then the other one automatically will be, it's very symmetric, so other one you should also be able to get. Can somebody tell me how A to the N, B to the N, A to the M is context-free?
Ma'am, we can have a production A to a capital A to small a, capital A, small b, and
once more, capital A to small a, then capital
small
B.
Ma'am, I was saying capital A to small a, concatenate capital A, concatenate small b.
Okay.
And then we can have a start symbol S that goes to either A or A is or S small a or epsilon.
S small b. S small b.
Ma'am, A or S small a or epsilon.
S small b, right? Can you repeat once more? S goes to?
Ma'am, shouldn't it be S small a for the first language?
So what are you saying? S is going to A or S small a or epsilon. This is what you're saying?
Yes, ma'am.
Okay. Let me see.
Ma'am, also, ma'am, A and another product, like the production of A should be A going to A, capital A, B, or epsilon.
Okay, just give me 1 minute. Yeah, I think this is correct. So if you first generate all the A's of A to the M, and then this A, then whatever, then the S that is remaining, you replace by A. With this, you generate A to the N, B to the N, right?
Yes, ma'am.
Okay, yeah. And similarly, by a very similar construction, you can generate this. You just swap this. You have A, sorry, let's call this B going to B A epsilon, and S going to B A S epsilon. This would give this language. Okay, so we can see that these two languages are context-free languages, but the intersection we have already shown to be not context-free. So context-free languages are not do not behave as well under closure properties as regular languages do. Okay, so the last thing that I want to look into is what is the relation between regular sets and context-free grammars? We saw that there are certain languages that are not regular sets, but that are context-free grammars. But does that immediately imply that regular sets are a subset of context-free grammars? Regular sets are a subset of context-free languages? I mean, there could be regular sets which are not accepted by context-free languages, right? So the only way of showing it formally is to show that every regular set has a context-free grammar. So what's your hunch? Should there be grammars, or are regular sets, I mean, does it look like this? Or does it look like this? Can you come up with a regular set like that, which is not a context-free language? Okay, so basically the correct picture is this. Regular sets are actually subsets of context-free languages. For any regular set, I will be able to give you a context-free grammar. So before that, I'm going to define regular grammars. So they are of two forms. One is right linear grammar, where all productions are of a specific kind. They must be of the form A going to WB or A going to W, where W belongs to sigma star. A and B are non-terminals. W goes to sigma star. So basically, any non-terminal symbol can be replaced by a string followed by another non-terminal symbol. It is possible that this non-terminal symbol does not exist. It can only be replaced by a string itself. Similarly, left linear grammar will just be all productions of the form A going to BW or A going to W, meaning that the non-terminal symbol will appear first and then it will be followed by a string. So it is not a combination. Or in right linear grammar, in the production, you have all the terminal symbols in the beginning followed by one non-terminal symbol, or maybe just only the terminal symbols. Similarly, here you have one non-terminal symbol and then the remaining are all terminal symbols. There are no non-terminals appearing in W anymore. So this is a very specific structure. And if a grammar is a right linear grammar or a left linear grammar, then we will be calling this grammar a regular grammar. Now, one thing to notice is that if you give me a right linear grammar, then if I construct a grammar of the following form, G dash is same non-terminal set, same terminal set, same start symbol. But the productions I go as follows. If A going to alpha reverse was in the original production set P, I will say A going to alpha is in my new production set. So if G was a right linear grammar, then G dash is going to be a left linear grammar. Okay. So please notice that they are not generating the same language. I'm just saying that if this is a right linear grammar, then G dash is a left linear grammar. Later on, we'll see the relation between the two languages, the language of G and the language of G dash. Okay, so if L belongs to, so now we will be looking at the relation between regular grammars and regular sets. So the first claim is a language that is generated by a regular grammar is a regular set. This is the first claim. So how do we do this? Let's assume that this regular grammar is a right linear grammar. You can give similar arguments for left linear grammar. We will be constructing an NFA with epsilon transitions for L of G. And the NFA will be of the following form. Q will be the set of states. We will define what Q corresponds to in terms of the grammar. Then you have sigma to the non-terminal, the set of non-terminal symbols will be the alphabet set for the NFA. We will get into what the transition function will be. If S was the start symbol, then then S, I mean a state corresponding to S will be the start state of this NFA. And the end state, the set of final states in the NFA will just be the singleton set corresponding to the epsilon string. So the NFA with epsilon transitions will basically be simulating the derivations of G. So let's specify what the states of Q will be. We are each state of Q corresponds to a suffix of a right hand side of a production. So if I had A going to alpha, so let's consider alpha dash to be a suffix of alpha. So then I will have a state corresponding to alpha dash in Q. And I will denote it, this state I will denote as alpha dash within brackets. Okay, so the state Q is denoted by alpha within bracket such that either alpha is S itself or it is a suffix of a right hand side of a production. So there will be a state for the start symbol S, or the other states correspond to the suffixes of a right hand side. Okay, now if L is a so now what remains is defining the transition function. So if A is a non-terminal, then delta of A at if you look at suppose you have a state like this, delta of A with on seeing epsilon, I mean, or not seeing epsilon, delta of A will make an epsilon transition to alpha if A going to alpha is a production. And if A is a terminal symbol and alpha is some string in sigma star union sigma star n, notice that this is the only way in which alpha can be if it's a suffix proper or if it's a right hand side of a production or a suffix of a right hand side of a production. Since these are regular grammars, alpha can only be of the form sigma star or sigma star n. So if look at delta A alpha upon reading A will go to the state alpha. Okay, now the thing is that alpha, the state alpha can belong to delta hat SW. W is the string that you're taking in. Alpha can belong to delta hat SW if two things occur. One is that alpha itself is S and W is epsilon. So then it will be of type 1. And the other case is S derives to XA and then A has a production to YA and XY is equal to W. So basically, if look at whatever is reachable from the state S, the start state S, upon reading W, alpha will belong to that. There is a special corner case where alpha is equal to S itself and W is equal to epsilon. The other case is, just from definition, the other case is that S has derived some sentential from form XA and A has a production A going to Y alpha and W is just this XY. This alpha is still remaining to be figured out in the derivation. So the non-terminal symbols you have read so far is exactly this W that you is exactly the input string W. That is the reason why whatever has to be figured out is alpha. That's the reason why alpha has been reached starting from the start state S upon reading these terminal symbols W. Okay, so let's build on that. You can prove this formally using the length of derivation, inducting on the length of derivation. This statement that I have made, you can prove it formally using the length of derivation as the for induction. But the intuition is as follows. If I want to simulate S going to S deriving alpha, suppose the first step is S going to WA. These are the only kinds of productions there are in regular grammar, in a right linear grammar. So suppose the first step is S going to WA. A could be A could be a non-terminal symbol or it could just be this W. So I am writing A to be N union epsilon. And W is a string of terminal symbols. So in the NFA, this is simulated by taking an epsilon transition from S to WA, from the state S to the state WA. So as if I have replaced, so in the derivations, I am replacing S by WA. This I am simulating in the NFA by making an epsilon transition, spontaneous transition from S to WA, as if S has been replaced by WA. Now let W be W1, W2 to Wn. Now let's say in the second step of simulation, I am reading W1. If I read W1, then I go from W1, W2, Wn(a) to W2, Wn(a). So this is the portion that still remains to be processed. This is where some further like non-terminals can be replaced by something else. This is the portion that remains to be processed in the derivation itself. So that's why in the state space, we are sort of moving towards the portion that still remains to be processed. So similarly, so if A is epsilon, suppose it was just S going to W, then at the n minus 1th step, we have reached the state Wn epsilon and we have defined delta Wn epsilon Wn to be epsilon itself. So we've reached the unique final state and we have generated the string W. Now what happens if A is equal to, the A is a non-terminal symbol. Then after n steps, we are at state A. Now, suppose we can further derive from A. Suppose there was a production A going to, let's say, W dash B. So now what I do is I take another epsilon transition from the state A to the state corresponding to W dash B. And then I continue simulating in that manner. So A was the portion that was remaining to be, there was a possibility that there were some further derivations that could be applied to A, and we take one such production, we take any such production and make an epsilon transition from A to the right hand side of that production. And therefore, we are sort of simulating the continuation of derivations starting from S. So is the intuition clear? So basically what we are doing is, suppose the suppose the first step was S going to WA. This W is W1 to WN. We are in the next step, we could have probably derived something from A. Maybe we could have done W dash B. Maybe this was the derivation in terms of the regular grammar. What we are doing in the NFA is the following. You have the state S. You can go by reading W1 to the state W2 up to WNA, and you keep doing this till you are at, let's say, WN, at the state WNA. You read WN and you are at state A. Now the portion that remains to be seen is W dash B. So from A you make an epsilon transition to, sorry, this is not, give me 1 minute. So you made a transition from S to WA first by epsilon transition. Then from WA you read W1 and go to W2 and so on. So from A, once you reach A, you make an epsilon transition to W dash B. And then you read the first, let's say, W dash 1, and you go to W dash 2 to W dash MB and so on. And you will take some further steps till you reach the state B. And then maybe you can add some more productions. If there was, let's say, W dash W2C, then you take some more things and finally come to C and so on. Notice that the string that you're reading, look at the labeled path, forgetting the epsilon. The labeled path is exactly, so far the labeled path is W dash W2. If you go further, the labeled path from S up to wherever you're going, the labeled path is going to be exactly the terminal symbols in the derivation in the regular grammar. Now at some point, if I don't have any non-terminal symbols left, then the label path will exactly correspond to a sentence in the regular grammar. And if I don't have any non-terminal symbols left, that means I have ended up in the final state epsilon, and therefore I have accepted this same string that was a sentence in the regular grammar. Okay, any questions? Okay, so then obviously the next step is to say whether a regular set has a regular grammar or not. So we know that this very specific format of context-free grammars, which are regular grammars, are only accept regular sets. But is the other way around also true? If this is true, then we can show that regular sets are a subset of context-free languages. So suppose L is a regular set, then what we will be showing is that L can be generated by a left linear grammar as well as a right linear grammar. So let's say, since it's a regular set, let's say it has a DFA M. So first we will assume that S does not belong to F, because if S belongs to F, then the empty string has to be accepted. So for the time being, let's assume that S does not belong to F. So this is how we will construct a right linear grammar. The set of non-terminal symbols will be exactly the set of states in M. The terminal symbols will be the same. Productions will correspond to the transition function. We will discuss that. And the start symbol is the same as the start state of M. What are the productions like? So if delta PA is equal to Q, then I will have a production P going to AQ. And if delta PA belongs to F, then I will also have a production P going to A. So if Q in particular was F, then I have an added production that says P is going to A, where Q is no longer there. Now you can see that delta hat PW is equal to Q. For the time being, let's assume that Q is not a final state. It is equal to Q if and only if P derives WQ. You can prove this formally, but this is also intuitively from the definition itself, you can see this will happen. And similarly, if Q is in F, then if Q is in F, then delta hat, the statement will just become delta hat PW equal to Q if and only if P derives W. Right? So then W is accepted by M if and only if it is generated by G. So we have shown that if S is not in a final state, then a regular set, then this regular set L has a right linear grammar. The other case remaining is what happens if S is in F, then we know that epsilon belongs to L, but the grammar that we constructed before generates L minus epsilon. You cannot generate epsilon with over here. This is a DFA that we are constructing. I mean, you cannot generate epsilon by the definition over here. So in order to generate, the only thing that is missing is epsilon. If the language, if S belongs to F, we know that epsilon is in the language. So we add this extra production S going to epsilon. And this will still remain a right linear grammar. That in the definition of a right linear grammar, this W belongs to sigma star. So A going to epsilon is allowed. This is not as strict as Chomsky, as the normal forms, where epsilon productions are not allowed. Okay, so it's still a right linear grammar. So therefore, if you give me a regular set, we have seen how to generate right linear grammars. Now, how do I generate a left linear grammar? I use the right linear grammar of L reverse. If L is a regular set, L reverse is also a regular set, and that would give, and I know how to generate a right linear grammar for a regular set just from the previous discussion. Use the right linear grammar of L reverse, and notice that I can, if G was the right linear grammar of L reverse, G dash is going to be the left linear grammar of L. This was the relation between G and G dash. Okay, if G was the right linear grammar of a language L, then G dash, which is constructed in this manner, is going to be the grammar for L reverse, and it will be a left linear grammar. Okay, so any questions? We have been able to show that regular sets are subsets of context-free languages, and they have very specific context-free grammar structures. That is, they have regular grammars. Do you have any questions regarding however much you have been taught in context-free grammars? Okay, so then on Thursday we have a tutorial on context-free grammars, and on Tuesday we will have the first test in flat. We are also considering 2 more tests. So we want to take 3 tests, one for finite automata, one for context-free languages, and finally the last one in your you have a reserved semester, you have a reserved week for your final exams. So we will be the plan is to test you on Turing machines in that semester, in that week. You are tested on finite automata in the mid-semester week, and sometime in March, maybe the second week or the third week, we will take one more exam that will be testing you on context-free languages. That way, I think the syllabus will also be manageable, and you will have enough tutorials in between, because now on context-free languages, you'll just have one tutorial on Thursday, and after that you will have to go into the exams. So we thought it will be fairer if we gave you some more tutorials and then took an exam maybe in the second or third week of March. I hope that's okay. And it will be within class, so you won't have to make time separately. Okay, so we'll be sending you an email maybe after the tutorial on Thursday regarding the logistics of the test on Tuesday. If you have any questions, you can ask me. Okay, then that's all for today. We'll meet on Thursday at 8. Thank you.
Thank you, Magali.